Welcome to the video on fractions. You have already had a chance to see a video introducing what you need to excel with fractions. And this video is going to be addressing questions from 4.1 of the Redwood's pre-algebra textbook. So we're looking at fractions here. And the first and one of the most important skills involved with fractions is knowing how to simplify the fractions. And you will see why this is important as you go through the chapter. So there's a little bit of history that is given here, and we can discuss this more later. But we know that the Egyptians were using fractions, right? We see hieroglyphics showing fractions involved. And the idea of fractions is, well, the concept of fractions is very critical to understanding any algebra, I would say, a lot of algebra concepts. And so, especially when you deal with rational expressions and rational equations, understanding fractions will be very important. So again, we know what numerators are and denominators. The numerator is the one on the top. If you are confused about or concerned about remembering which one is the numerator and which one is the denominator, just think of it this way. Down is this is down, and so we could call that D for down and D for denominator. So we have the numerator and the denominator, and those are if I use like 1 over 2, this would be called a proper fraction. And the idea here is that if you had something like 3 over 2, that would be called an improper fraction. Now, do you see why one is called proper and one is called improper? It has to do with which one is bigger, the denominator or the numerator. Now, there's nothing wrong with being an improper fraction. There is a time and a place to have improper fractions as your answer. But there's also a time and a place to have mixed numbers, which would be a situation like that. Now you have a mixed number or mixed fraction there. So we have the numerator and denominator. That's very important. The first key thing you discuss here is equivalent fractions. Equivalent fractions. So equivalent fractions, basically, if you have 1 over 2, that's a half, right? You say that's half. But what if you have 4 over 8? Well, that's equivalent, right? And the key here is if you had 8 boxes, right? And this is not drawn to scale, but 1, 2, 3, 4, 5, 6, 7, 8. If you had 8 boxes and I said 4 over 8, you would be addressing 4 out of the 8. And if you only had 2 boxes and it's 1 over 2, notice that the quantity is the same of what is shaded, right? In a sense, if you were to look at it like this. Think of like a chocolate bar. You can use that to represent the chocolate bars there. But hope I'm not making you hungry. Let's get back on track here. But yeah, so that's how you have, you can divide it. You can have this as 4 over 8, or you can have 1 over 2, right? Very good. So your book goes on in page 231 to talk about fractions, equivalent fractions, and that's a very important skill to have. The key about equivalent fractions is that whatever you do to the numerator, you do the denominator as well. So for example, if you have 1 over 2, if you multiply the top and the bottom here by 2 over 2, then you would have 2 over 4. So 1 over 2 and 2 over 4 will be equivalent because you multiplied both the numerator and the denominator by the same number. So that's how we get an equivalent fraction situation. If we multiply by the same number, we will get an equivalent fraction. So that's how we create equivalent fractions. Now, in your book on page 233, it uses an example of a over b, and then it does this, and then it multiplies them by x. Now, remember, the reason why we use letters in math, one of the main reasons is to show generality, is to show that no matter what numbers are plugged in for those letters, you will still get the same, you would still get the same outcome. So, for example, if you had 3 over 4 here, and we wrote equals 3 over 4, so notice A is 3 and B is 4. So you have 3 over 4, and we're multiplying by x. So now we're going to pick a number x. Let's say 5. So if I do this, now remember the dot represents a multiplication. So you have 3 times 5, which is 15, and 4 times 5, which is 20. So 15 over 20 and 3 over 4 are the same. They're equivalent. Why? Because we multiplied both the numerator and the denominator by the same number. That's why they're equivalent, and that's how we create an equivalent fraction. If we want to reduce a fraction, which is what you've seen simplifying fractions, then what you do is, or another way of creating equivalent fractions, I would say, or simplifying a fraction, is where you take a situation like, let's say 4 over 16. 4 over 16 have a common factor, right? Or they have common factors. So if you want to reduce this, right, to its simplest forms, or its simplest form, if you want to reduce it to simplest form, then what you do is you divide both the numerator and the denominator by what they have in common. So like 4. So that becomes 1 over 4. So basically, if you do that, 1 over 4 is the same as 4 over 16. You reduced 4 over 16. You brought it to its simplest form or its lowest terms. And that is how you were able to create a different equivalent fraction for 4 over 16. Now, here's what's interesting. 4 over 16, notice I just used 4 right away. But what if you don't know what the greatest common factor between the numerator and the denominator is? What you do is you can just go ahead and start with what you know. You know that 2 is a common factor, right? I mean, 2 goes into 4 and 2 goes into 16. So you could use 2 right away, and then you get 2 over 8. That's okay. And then you do divide it by 2 again, and now you have 1 over 4. So notice you could go step by step. You divide by 2, divide by 2 again, right? And so that's how we get, simplified to 1 over 4. But as you get more comfortable with numbers and greatest common factors and so on, you can automatically remove what that greatest common factor is. And that comes with practice. So just keep practicing and you will get more comfortable with, simplifying fractions. So that's good to keep in mind. Then we're going to introduce a new term here. We're going to talk about the greatest common divisor. That's one way they call it here. If you know, greatest means, of course, the biggest of something. Common means that something that they that they have in common. And then divisor is think of it as a factor in a sense. So some people call this a greatest common factor also. So this is greatest common divisor, or if I said greatest common factor, right? Because the factors of 6 are 1, 2, and I'm going to actually put a note like this: 1, 2, 3, and 6. Random fact, by the way, there's something called a perfect number. A perfect number is a number whereby the factors of that number, apart from the number itself, so in this case 1, 2, and 6, add to give you that number. That's an interesting observation. So like 1 plus 2 plus 3 is actually 6. So 6 is a perfect number. And again, this is just a quick commercial, but just wanted you to keep that in mind. It's an interesting observation that some mathematicians have brought to our attention, that some numbers are called perfect numbers. But okay, so when you have a number, you can break it down to its, what are the factors that make up that number, or you can talk about what is the prime factorization of that number. So for example, 6, the prime factorization of 6 is 2 times 3, right? 2 times 3. Now remember, when you're dealing with fractions, it's important that you remember your prime factorizations. It's going to be helpful in finding the lowest common denominator and so on. So just keep that in mind. So let's find let's look at the greatest common divisor of 12 and 14. So 12 is 2, right? The factors of 12 include, 1, 2, 3, 4, 6, and 12. Those are the factors of 12. The factors of 14 are 1, 2, and 7, right? So we know that, of course, they share a 1, they share a 2, and they don't share anything else in common. So the greatest common factor of 12 and 14 is actually 2. 2 is the only thing they both share. Now, they share 1 also, but 2 is a significant thing we're looking at here. But you could say 2 times 1, which is 2. I'll explain why I did the 2 times 1 here in my next step. If you take 12 and you prime factorize it, you would actually get 2 times 2 times 3. If you take 14 and you prime factorize it, you actually get 2 times 7. Growing up, I remember when we learned this, we would circle the 2 that is common between them, and then we would say that the greatest common factor is 2. So that's how we find the greatest common factor. That's one way to look at this. And so I would encourage you to, again, make sure you're comfortable with prime factorization. Of course, you don't need to know all the prime numbers, but it's good to know that 2, 3, 5, 7, 11, 13, 17, and 19 are prime numbers, right? That's a good set of numbers to start with. in your book that we provide you, the free resource, Tools for Master Mathematics, you can get, you can see the list of, the prime numbers below 100. And it's just a fun activity. You can use, there's this approach out in math, the sieve of Eratosthenes. I'm sorry, I might have mispronounced his name, but that is one way. So it would be sieve of Eratosthenes. That's how, sieve of Eratosthenes. If you look that up, you can see how we can use that to find prime numbers below 100. So, but it's just good to know at least the first set of prime numbers. The idea is these numbers are only divisible by themselves and 1. Now, keep in mind that 1 is not a prime number. It's neither prime nor composite. On the ACT exam, which students take down the road, at some point, I recommend they take it as soon as they can, even if it's 8th or 9th grade, to get experience. And some people have scored quite high, actually, up to what they want in that level. But I recommend in studying for the ACT, one of the things that you will learn is the importance of knowing your prime numbers and working with them. And one of those questions that I've seen in a few spots on some of these types of standardized tests is, what is a prime number that is also an even number, for example? Well, that's 2. 2 is the only number that is prime and even. And then 1 is neither prime nor composite. Something to keep in mind. Your book goes on to talk about reducing a fraction to lowest terms. That is, there's videos, that I've made for you, and you would see that in this section, in this chapter as you work through. So it talks about reducing numbers, right, to the reducing fractions to its lowest terms. But then I want to end. I want to talk about reducing fractions with variables. Let me talk about that for a few minutes here, and then we'll begin to wrap up this section. So we'll talk about that, and then we'll look at anything else we have to discuss. So let's look at an example here. So we're reducing fractions with variables, right? And what you're actually using to do this, right? So when you're reducing fractions with variables, what you're actually doing here is using a principle that you're going to learn later in algebra. Part of what's going to be helpful here, and that's called the rules of exponents. That principle is going to make this work much easier. But let's say you don't know what those principles are, and that's okay. Let's look at this. 25a cubed b squared divided by 45 a cubed b cubed. Okay, if you have a situation like this, according to your book, part of what you need to do is you could just write out the number, like the prime factorized version of these numbers. So 25 is 5 times 5, so we write 5 times 5, and then you write out the letters in question. And then for the 45, you can prime factorize, you get 9 times 5, and you get 3 times 3. So you get 3 times 3 times 3 times 5, and then times a times a times a, and then b times b times b. You can cancel what they have in common, right? Because each of these are multiplying one another. So you are allowed to cancel, right? So this 2 will cancel these 2, and then 1, 2, 3 will cancel 1, 2, 3. The 5 will cancel the 5. So what you're left with is this 5 over here, and nothing in the numerator. In the denominator, you have 3 times 3, which is 9. And you have this b over here. So that will be the answer to the problem. So you can write out the prime factorized version of the numbers, write out the letters, and then you can cancel. So that is important to keep in mind. On page 238, your book goes on to talk about mathematical notation and explains some details there, which I encourage you to read. And then, so it talks about inline mathematical notation. 14x divided by 15y is called an inline mathematical notation when the same expression is centered on its own line, as in, and it shows it 14x or 15y. So they show you that. Let's see. So earlier on it shows 14x divided by 15y. So that's called an inline notation when the same expression is centered on its own line, as in this situation. Then the type of notation is called displayed mathematical notation. Just something to keep in mind. I wouldn't worry if you forget your terminology on this specific issue. So it goes on to give you a little more background there. And then we move on to page 239. It talks about equivalent fractions in higher terms. We discussed some of this earlier on. You can take a number and make it bigger. So example 6, Well, the number, I mean, individually, each of these numbers will have maybe bigger numbers, but the fractions will be equivalent and the same. So number 6 said express 3 over 5 as an equivalent fraction having denominator 20. Part of what they want you to do is they want the denominator to change to 20. So then you ask, what do you do here to make that happen? Do the same thing in the numerator. So you multiplied the denominator by 4. That was how you got 20. So you have to multiply the numerator by 4, and that's going to give you 12. Another example, they said express 2 over 3 as an equivalent fraction having denominator of 21. So if you have 2 over 3 and someone says, can you make the denominator 21? Yes, we can by multiplying by 7. But we would have to multiply by 7 in the numerator as well. So notice that the reason why you're learning this particular skill is that there are some times in math where you need to convert the denominator to a certain number for a reason, especially when you're adding and subtracting fractions. And therefore, whatever you do to the denominator, make sure you do it to the numerator. And then the next example 7, next to it says express 5 as an equivalent fraction having denominator 7. So express 5 as an equivalent fraction having denominator 7. Keep in mind that 5 is essentially 5 over 1. A number by itself, if I just say 3, it is technically, you could write it as 3 over 1, right? And you will see why there's times where you want to do that, because then in this case, they say express 5 as an equivalent fraction having denominator of 7. So if you want to have a denominator of 7, you have to multiply by 7 to get that denominator to be 7. But that means you have to multiply the numerator as well in order to get that 35, because whatever you do to the denominator, you have to do to the numerator. Very good. So that's the same idea we use in example 8. However, with example 8, now I'm doing the problem that says you try it. I'm going to provide the explanation. It says express 3 over 8, right, as an equivalent fraction having a denominator of 24a. So here's the trick. I'll tell you, or here's not a trick, but here's the rule. If you want this to become that, then technically you multiply this by something to give you this. If you want to know what that something is, one of the ways you can do that is actually say, what is 24a divided by 8? Right? 8 goes into 24 3 times, right? So that means you multiplied by 3a to get 24a. And if you multiply the denominator by 3a, that means you have to multiply the numerator by 3a, and that actually gives you 9a. So 9a over 24a would be the answer to that problem. Your book goes on to talk about negative fractions. Again, we work with negative fractions in similar ways as we work with integers, in terms of the rules that, if you have two negative numbers multiplying, you get a positive. But it is important for notation purposes to keep in mind that 3 over 4, okay, negative 3 over 4 is actually the same thing in value and quantity as 3 over negative 4, which would be the same thing as putting a negative in front of both of them. So all these are, the fraction in each one of those would be negative at the end of the day. So keep that in mind. It's all the same for that. And that applies to all fractions. If you have negative 11 over 12, it's the same thing in quantity that I would be dealing with if I had it this way. And if I put the negative in front of the negative 11 over 12. Negative 5 over 6, you have negative 5 over 6. You have negative with the 5 over 6. And actually, we're going to move this negative here. We're going to move it to the denominator. Okay, it's all the same. Very good. So reducing fractions is a critical skill to know, and that's where we're going to finish off our section. So we're going to be reducing fractions. So reducing fractions. So we have 14y to the 10th divided by negative, let's go with 21y squared. So this becomes 2 times 7, technically, right? 14 is 2 times 7. And 21 is 3 times 7. So we'll put a negative in front here. And then we have 10y's. Why did I do that? I don't know. I could have chosen a different problem, but I just chose to use 10y's. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then in the denominator, you have 2. So 2 of them will cancel 2, leaving you with 8, right? So the 7s will cancel. So you have 2 divided by that negative 3 there, and then y to the 8th this is the same as a negative 2y to the 8 over 3. This I would generally see a lot of problems like this with the negative in front as far as a solution, or you can put that negative with the 2. Leaving the negative in the denominator just doesn't look as good, but it is the same in terms of value, something to keep in mind. Let's finish with one last question here. If we have negative 14a cubed b squared divided by negative 7a squared b cubed. If you have a situation like this, keep in mind the negatives can cancel right away. The 14 is 2 times 7, and then you have 3 a's and 2 b's. And then you have 7 in the denominator with 2 a's and 3 b's. 2 of the b's will cancel, right? And 2 of the a's will cancel. So now we have 14. Oh, sorry, the 7's canceled. So you have 2a divided by b. And that will be the answer to that problem. So we've looked at finding, we're going to talk a little more about finding greatest common divisor. But we've looked at greatest common divisor. We've looked at reducing fractions. We've looked at creating equivalent fractions. And we've reduced fractions to lowest terms. And there's just a lot of extra practice problems here for us to work with. So there are about 102 problems. I want to encourage you to take your time, work through as many problems as you need to. If you want to do if you could do the odd problems, I would highly recommend that, from number 1 to 101. There is a word problem at the end there with number 101, and that could just be for fun. But let me know if you have any questions on that, or let me know if you have any questions on any of the sections. So feel free to try all the sections, each of the sections. And if you're stuck on a particular section, move on to the next one, but send me an email right away letting me know which one you would like more examples on. Thank you for your time and have a wonderful day.